So back to power series. We played around with series centered at 0 yesterday. Let's play with a new center today. So there's going to be a problem similar to this in your homework. I got the sum as n goes from 1 to infinity of n to the 7th power times x plus 10 to the nth power divided by 10 to the nth power times n to the power 23 thirds. That's a beauty. And so we are going to attempt to find the interval of convergence. Okay, so for what numbers can we plug in an x value and this infinitely long polynomial will actually have an answer for us? First thing you should always do is just kind of think about it for just a second. Now, writing these terms out with power series isn't always as important as it is with regular series. But I want to say, okay, well, it's not just an x to the nth, right? It's an x plus 10 to the nth. So what does the x plus 10 tell us about the series? Well, if we think about functions, if we started off with a function f of x, and we then rewrite the function, let's say g of x, by replacing x with x plus 10. Anybody remember what happens graphically when you replace x with x plus 10? It's a shift, yeah, which direction? Yeah, negative direction. So this is a shift left 10. Okay. So what it tells me is when I do find my interval, negative 10 is going to be the center of that interval. And then I'm hoping to find some radius that I can jump in each direction and end up with an interval of numbers for which this thing converges. Okay. There are some series that people find that just don't ever converge. A series sometimes it converge at just a single point. Other times it can be infinitely convergent for every number possible. So there's all kinds of options out there. Okay, so I know that this is centered in a different spot. Okay, so this one's centered at negative 10. Other thing I always ask myself is, can I clean this up before I continue? And so I'm looking for anything that might clean up. And what jumped out at me after I started working it the first time was that, hey, I get n to a power in the top and the bottom. I can just bring those together, right? We have a rule for that. So I'm just going to do that right away too. So if it turns out you can do a little algebra before you continue, always a good idea. Otherwise you have more work to do later. So what happens if I just take n to the 7th divided by n to the 23 thirds? Well, that would be n to the 7 minus 23 thirds. Let's see, 7 is 21 thirds. So it's going to be negative 2 thirds, which I would probably rather write as 1 over n to the 2 thirds. So I don't have to worry about negative exponents. There's nothing wrong with negative exponents, but somehow we were biased by them by our previous teachers. But they're actually okay. Okay, so I'm going to rewrite the series, cleaning up this spot, and then we'll actually apply the ratio test, which is our standard thing to do here. So now I'm looking at the sum as n goes from 1 to infinity of x plus 10 to the power n divided by 10 to the n times n to the 2 thirds is what we cleaned this up to be. And now we're ready for the ratio test. So for the ratio test, I want the absolute value of the n plus 1th term. So that would be x plus 10 to the n plus 1 over 10 to the n plus 1, and then n plus 1 to the 2 thirds times the reciprocal of the nth term, 10 to the n to the 2 thirds, that is an n, there we go, it's a little better, x plus 10 to the n. Now, there are no alternating terms like a -1 at the moment, but I do need the absolute value because at the moment I don't know what x is. X can be any number, so I have to keep the absolute value in there for now. And then what gets to get crushed here? Well, 10 to the n goes into 10 to the n plus 1 10 times. And then x plus 10 to the n goes into x plus 10 to the n plus 1, leaving behind an x plus 10. And there's not too much I can do with the n to the 2/3 and n plus 1 to the 2/3, except I could note they are the same power. So I could write that as, instead of a fraction of powers, the power of a fraction. That makes sense? So what I'm saying here is, I think what I can do is say, I have the absolute value of x plus 10 times n over n plus 1 to the 2/3. Oh, what am I missing? Divide by 10. I got everything now. Let's see, check, 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 check. Okay, I got everything now. Oh, good. Another contestant. Welcome. Okay, so we've cleaned it up as much as we can. Now it's ready to take the limit of that thing. So let's see. I'm just going to write it this way. As n goes to infinity, what is this thing going to? Well, the only n's are right here. What's n over n plus 1 doing as n gets big? It's going to 1. Excellent. All right, it's a polynomial, same degree top and bottom. Okay. So like a billion divided by a billion and 1, pretty close to 1. Right? They're about the same number. So this sucker here is going to 1. So that means for my limit, I'm left with the absolute value of x plus 10 over 10 after completing the ratio test. Ratio test says we have convergence of this limit when what is true? When this is less than 1, when that's less than 1. So I'm going to bring that to a new page to clean up. So x plus 10 over 10 in absolute value has to be less than 1. 10 is a positive constant here. I can multiply both sides by it. So I'll get the absolute value of x plus 10 is less than 10. I'm going to rewrite this one more time to do it. Remember the geometric interpretation we talked about before? My claim is this is x minus -10 in absolute value is less than 10. And anytime you have a difference in an absolute value, you're talking about a distance. So this tells me geometrically the distance between x and -10 must be less than 10. In other words, x is a number that's no more than 10 units from -10. Does the -10 here make sense according to the shift we talked about earlier? Yeah, so what this is telling me is on the number line, -10 is the center of my interval. My radius of convergence is 10, and in a lot of these problems you're asked, what's the radius of convergence? And that's always nice to know, but we also want the interval. So that means if I jump 10 to the right, I'll end up at 0, and if I jump 10 to the left, I'll end up at what, -20? And so this is my interval so far. So according to the ratio test, if I pick any number between -20 and 0, and I plug it in for x, this infinitely long sequence of numbers, sum of numbers, excuse me, should converge to some answer. Today we're going to start finding what those answers are. What the ratio test doesn't tell me is I have no idea what's happening at each endpoint, so I got to go back and check each of those separately. So we have a radius of convergence, we have part of our interval. Next thing to do is test the endpoints. So my original series, remember, in the cleaned up form at least, n equals 1 to infinity of x plus 10 to the n over 10 to the n times n to the 2/3. I think I got that right. So far we know that x has to be between -20 and 0 according to the ratio test. We have to check what's happening at 0 and at -20. So let's do -20 first. If x equals -20, then I'm going to have the sum as n goes from 1 to infinity. Let's see, -20 plus 10 is -10. So I'll have a -10 to the n in the top. There's a 10 to the n in the bottom, and then n to the 2/3. Does that clean up a little bit algebraically? Yeah, the 10 to the n, -10 to the n over 10 to the n, that can be cleaned up to be a -1 to the n, right? So I can rewrite this again as the sum as n goes from 1 to infinity of -1 to the n over n to the 2/3. Well, let's see, what do we know about this? Well, we know it's strictly alternating, so I'm thinking alternating series test. So 1, it is strictly alternating. And if I take the limit of the non-alternating part, 1 over n to the 2/3, well, the denominator is getting bigger and the numerator is fixed at 1, so this thing does go to 0. And so those two conditions mean this is convergent. So now I can say, hey, it's less than or equal to on the left side. Now, what's going to happen on the right side when I plug in 0 for x? I'm going to get 10 to the n in the top, dividing by 10 to the n, which means I lose the alternating. It's a p series, but p is less than 1, which means this grows slower. Let's see. It's worse than the harmonic series. Yeah. So it's going to diverge on the other side. So we can just kind of see that. So I'm just going to make a little note in red here, because we kind of have the work here for it. If x equals 0, then this is a p series. P equals 2/3, which is less than 1, which implies divergence. So then this is my final interval right there. I have it converging on the left side, but diverging on the right side. And it converges at any number in between according to the ratio test. And even better, according to the ratio test, with the numbers in the interval, because the ratio tests use the absolute value around them, it converges absolutely, which means it converges in absolute value. Who cares? Well, the best thing about converging in absolute value is that it doesn't matter if you reorder the terms somehow to try and test what the number is, you'll get the same answer. However, on the endpoint here, the absolute value of this guy doesn't converge, which means when trying to find what number this converges to, we aren't allowed to rearrange the terms. Otherwise, we could get different answers than what it really goes to. All right. So just from a computational point of view, that's important. Oh, that was exciting. All right, so that's about the worst your homework from 10.8 gets, Introduction to Power Series. So we're going to move on a little bit more with Power Series by focusing on geometric series. So remember geometric series, if r is less than 1 in absolute value, 1 plus r squared plus r cubed forever and ever and ever is always going to be equal to 1 over 1 minus r. Okay, and the point I made the other day is we can replace r with x if we want, in which case this is a function. Okay, but r is a nice variable. So what I've developed here is a power series that's a function of r. That function is infinitely long as a polynomial. An alternate version of this function is to say it's just 1 over 1 minus r. Okay. Just to double check that, I'm going to graph both of these, see what they look like. I'm going to use GeoGebra because it's slightly easier to type in series for me there. So first thing I'm going to do is I'm going to graph 1 over 1 minus x. Okay. Something to consider here, the series I'm about to write is only convergent between x equals -1 and x equals 1. So I'm stuck between these two lines here. All right. So now if I do a sum sequence, I like that one. My sequence is just x raised to the power n. My variable is n. What's my start value here? 0, good job. And my n value, let's go out 10 terms. So we'll do the 10th partial sum. Okay. So can you see I got this red curve sitting right on top of the green curve. So they match for a while, but notice then they stop matching. Why? Well, I only went out 10 terms. The theory says I have to go out forever for it to really look good. Well, I wonder how far we can push. Can GeoGebra handle 100 term polynomial? Ooh, yeah, look at that, pretty tight. Okay, and if we look up here, they look like they're pretty tight for a while. I can't see the difference between the steepness makes it tough to track. But there's a red and a green curve living next to each other. Oh, I can kind of see them starting to separate there. Oh yeah, we got to zoom way in though. I don't even know what my number line looks like now. It's pretty tight. Okay, so they're not perfect match, but they're pretty darn close. All right, so how do I zoom back out? I guess I just have to do that. And then get back down here. Ooh, what did I do? Where am I? Where in the universe are we? Come on. Okay. Let's just do it this way. No, this way, that way. I'm having all kinds of trouble here. Ah, that's what I want right there. Okay. So we're going to just make x go from, let's see, -1 to 2 tab. Well, I'm just not having fun with technology today. And y, you can go from, how about 0 to 5. Okay, so now I can see the curve again. All right, so what we're going to do is we're just going to mess with this function and see what we can get to come out of it. So as far as playing with power series go, you can do substitutions on power series. So the kinds of ways we're going to manipulate power series are doing substitutions. So we could replace x with a -x and see what happens. We could replace x with an x squared, or a 3x, or an x minus 1. 2, we can just do regular arithmetic kind of stuff. So we can add numbers to the, like add 1 to it, add 2 to it. We can multiply it by 17. We can do things like that. 3, if it's convergent, we can differentiate the power series. And again, if it's convergent, we can integrate the power series. And these manipulations are going to allow us to make some new series and solve some problems from earlier in the course that we didn't know. Like we had that series that looked like it was adding up to 3/16. We're going to prove that today. Okay. So first manipulation I'm going to make is I'm going to let r equal negative x. So in my formula, 1 over 1 minus r equals 1 plus r squared plus r cubed and so on. Let's rewrite it. So if I replace r with negative x, then I'm going to get 1 over 1 plus x instead. And then over here, I'm going to get a 1 minus an x. If I square a negative, it's a positive x squared. If I cube a negative, it's negative. So I end up with an alternating power series, which I could say is the sum as n equals 0 to infinity of negative 1 to the power n over, nope, no over anything. It's just times x to the n. Let's see. Come on, eraser. There you go. So slightly different series. I could then take this series and I could apply another one. Let's use y as my variable. Let's let y equal x minus 1. So if I do that, 1 over, oh, is that what I want to do? I want to let x equal y minus 1. Sorry, I wrote that backwards. All right, so if I replace x here with a y minus 1, then I'm going to get 1 plus y minus 1, which is just y. So I'm going to get 1 over y equals, and over here, I'm going to get 1 minus, I got to put stuff in parentheses, y minus 1 plus y minus 1 squared plus, oops, minus y minus 1 cubed. See a pattern there? Question, what was the center of my first series? Zero? Zero, yeah. It was centered at 0 and had a radius of 1. So the interval of convergence was absolute value of r is less than 1. When you do a substitution, the substitution affects the interval. So when I substitute in, what do? I replaced r with negative x. For this second one here, I'm going to get the absolute value of negative x is less than 1. Okay, what's the absolute value of negative x? Well, it's the same as the absolute value of x. So I get the same interval. But down here, the interval changes a little because I replaced x with y minus 1. So for this one over here, the interval is going to be y minus 1 is less than 1. What's the center now? The center, yeah, I shifted it 1 to the right. The center is now 1. So for this series at the top, just note it was centered at x equals 0. This one maintained that same center at x equals 0. This one, however, is a shift, and so its center is now at 1. So under certain substitutions, your interval is going to change. Sometimes the radius will change. Sometimes it'll shift left or right. Also, the endpoints might change behavior. If it diverged at both, it might still diverge at both. It could converge at both. It could do one or the other. So I'm going to skip testing endpoints for now just to play some more. But it is possible that although the endpoints were divergent here and here maybe they converge one or the other. And the only way to know is to plug the endpoint in and see what happens. Okay. Now let's think about why the shift here was essential by just looking at the graph of 1 over. the reciprocal function. So let's turn u off and turn u off, turn u off. So I just want to graph 1 over x. And so we're kind of pretty familiar with this function. Let's see, go away. Go, all right. Let's see, move tool. All right, so here's our function here. At x equals 0, it doesn't exist, right? There's a vertical asymptote. So I couldn't center this at 0, because what is f of 0 here? It's undefined, okay? So I had to center it at some other place, and here it just kind of worked out nice that I shifted it 1 to the right, and now I have a series for 1 over x. So I'm just going to check to see if that really works. So if I plug in my sum sequence, my sequence is, let's say it's alternating, right? So I'm going to have a -1 raised to the n times x minus 1 raised to the n. And that's all there was to our series, right? So then I have a comma, n is my variable, starting at 0, and let's go out 10 terms. So that's that blue curve here. And you can see the blue curve, it fits pretty tight on top of the red one. So let's see, what was the radius of our series? The center was 1, the radius is also 1. So this thing should fit fairly tight between what two numbers? Between 0 and 2. Yeah, I should find it fits pretty tight between 0 and 2. And then I start to lose it. Now I'm only going out 10 terms, so I'm losing it quite a bit before 2 there. But remember, my center is at 1 here. So if I say, hey, GeoGebra, just give me some more terms, like before, if I say go out 100 terms, then it's going to get a lot tighter toward the edge there. Okay. So we found a power series representation for 1 over x, which is kind of cool. All right, let's take it a little farther. Other things I could do, let's go back to play with this guy here. So we have the series 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed. Going on for a while. We could sub in x squared if we wanted to. My colors went away. I'm running out of letters. Let's use, no, what did I just do? Yeah. How about a u? Let's let x equal u squared. So then I'm going to get 1 over 1 plus u squared is equal to what? 1 minus u squared plus u to the 4th minus u to the 6th. And it's going to keep going on and on like that. Because I'm replacing every x with an x squared. Could we write a summation notation for that? Let's try. The sum as n goes from 0 to infinity. Let's see. Well, we have our -1 hanging out to the n. That should still be okay. How do I make n even? Yeah, 2n. So let's just double check if this works. Here n is 0, 1, 2, and 3. So if n equals 3, I'll get -1 cubed. That works. And 3 times 2 is 6. Yeah, that wasn't too bad. Sometimes it's easy to look at a list of a sum like this and write a formula for it. Other times it's not so easy. We'll see some next week that it's like, ooh, I don't think I want to do that. But for now we can. All right, other things I mentioned we can do with these is we can differentiate them and integrate them. So let's try that for fun. Let's integrate this one. We'll differentiate a different one. New color. So what happens if I integrate 1 over 1 plus u squared du? Does anybody remember what that sucker is? Make a wild guess. It's not a logarithm. Think back to last term. We had this memorized for a little while last term. It's a trigonometric function, not secant squared, but you're getting warm. Warmer. Tangent is warmer.
It's
Arctangent. Yeah, this is the arctangent. Okay, so this is the arctangent of u. Okay, plus c. Right, we got that plus c to worry about there. Now, the rules about integrating and differentiating series, you can integrate and differentiate term by term through their polynomials as long as it's in their convergent region. Okay, so that's fine. I'll just stay. I won't pick any u's outside of the convergent region. Oh gosh, what is the interval over here? We never talked about that. Well, let's see. This guy in blue had an interval of, oops, absolute value of x had to be less than 1. We just replaced x with a u squared. So that gives me an interval of absolute value of u squared has to be less than 1. Now, oh, interesting, u squared is always positive, so we don't need, or it's non-negative, I don't need the absolute value. So that could lead me to say that u squared has to be less than 1. How do we get rid of a square? Take the square root. Okay, so then I'll have the square root of u squared is less than the square root of 1. What's the square root of u squared? Nope, it's not u. Close. Is absolute value of u. Now you can't do the plus or minus because that screws up the inequality. So it's the absolute value of u. Man, that thing is ubiquitous. Okay, so we didn't really change the interval much, but we might have changed the endpoints. We don't know the endpoints. We haven't tested those. We'll do those on the arctangent. All right, so we still have a radius of 1. We're still centered at 0. Okay, no big whoop. But what we want to do is we want to compare the integral on the left to the integral on the right. So we have to integrate term by term the right side. So new page, we need to integrate 1 minus x squared plus x to the 4th minus x to the 6th plus blah, blah, blah. And then we're gonna, sometime we're gonna have a negative 1 to the, I'm gonna call it a k times x to the 2k plus, and it keeps going forever and ever, dx. And I'm doing a definite integral here. I'm not worried about the boundaries at the moment, so I don't have any. All right, antiderivative for 1. Oh, we were using u's over there. I switched to x's. Oh well, we're sticking with x's now. So that would just be x, right? And then minus integral increases the power of a polynomial. So that's going to be an x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, la, 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 all the way over to negative 1 to the k. And then let's see, I'm increasing 2k by 1. So that's going to give me x to the 2k plus 1 divided by 2k plus 1. And this thing just, again, keeps going forever and ever. But the cool thing about, knowing the summation version is that then I have a summation version for the integral. That usually works out pretty good. All right, so let's see. This is supposed to be, and usually I put the plus c on this side. It doesn't really matter. So my claim is this thing right here is equal to the arc tangent of x. I would like to figure out what c is. So let's see. What's the center of this? The series I started with? It was centered at 0. So usually I plug in the center to see what happens. So if I plug in x equals 0 here, then on the left side, I'm going to have the arctangent, or at least on one side, of 0. On the other side, all these guys just say, hey, 0, goodbye. And so arctangent has to equal c. What's the arctangent of 0? Tangent of what angle has 0 as the answer? 0. Yeah, it's 0. So this tells me the constant is 0. So now I know a series for the arctangent. So this is where things get fun. Check this out. This is awesome. So the arctangent of x is equal to this sum right here. So starting with x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Keep going all the way down the road there. In summation notation, if I wanted to write that, it would be the sum as, let's see, n goes from 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. Let's make sure I got that right. My claim is that this is when n is 0, 1, and 2. So let's see. If n equals 2, -1 to the second is positive, so that checks. And then 2 times 2 plus 1 is 5. Okay, yeah, I got it right. Hey. All right. Now we're going to have a little more fun. We actually saw this series in class one day, but we didn't know it was connected to the arctangent. What we saw in class one day was a 1 minus a 1/3 plus a 1/5 minus a 1/7, and so on. We saw that series in class. Now we know that it is equal to the arctangent of 1. Ooh, arctangent of 1. That means tangent of what angle equals 1. So for what angle is the slope 1? Think unit circle. There's a line with a slope of 1 through the unit circle. What angle is that? What is it? Pi over 4. Yeah, this must be pi over 4. Let's test it out. All right. Okay, let's see. Where should we go to test it? Desmos, Wolfram, or GeoGebra? Wolfram, good choice. All right, so I'm going to go to Wolfram Alpha. And I'm going to say, can you please sum for me? No, what do I want? I want -1 to the n, oops, to the n, times what? Divided by, oops, so divided by an odd number of the form 2n plus 1. And oops, let's do that from 0 to, let's go the first 100 terms, see what it comes out like. Otherwise, Wolfram Alpha will spoil the fun and tell us it's pi over 4. Uh-oh, I typed something wrong. Oh, parentheses, right. It gives me the fraction version. There's the decimal version, 0.7878. Interesting. If I just ditch boundaries, Wolfram Alpha will take it to infinity for me. And if it recognizes it, it will say, oh yeah, that's pi over 4, 0.785-ish. Okay. I went out 100 terms. I got it to 2 decimal places. So one thing about this series, it is slow growing. 1,000 terms would give us 3 decimal places. 10,000 terms, 4 decimal places. Yeah, it's a wicked slow growing series. It's painfully slow. There are quicker ways to calculate what pi over 4 is. But think about it. How did we calculate places of pi before? Before calculators. How did we do it? Tricks like this is how we did it. Some person sitting with a big notebook adding and subtracting fractions over and over again. And hey, he did 10,000 of them. He got 4 decimal places of pi correct. And he only had to add 10,000 fractions. Okay. So that's not really how they did it. There are better ways to do it than this. But we're just stabbing at, like, how the heck did people figure this stuff out? Okay. All right, let's do another one. We got a little more time. I promised that sequence from the other day. Okay, so how am I going to get that one? What is my trick? My trick is to do an integral. We just did an integral. I wanted to do a derivative. Oh, good. Yes. No, we're going to do a derivative. Haha. Okay. Let's take, did I get that right? Sorry. Yeah. Go back to our original here. 1 over 1 minus x equals 1 plus x squared plus x cubed, and so on. Eventually, we have an x to the k, and it keeps going. We're going to differentiate this. So what is the derivative with respect to x of 1 over 1 minus x? Well, that's really the derivative with respect to x of 1 minus x to the power negative 1, right? So I could use the chain rule and the power rule to do this. So let's see, what do I get? Which one do I want? The power rule says drop the power by 1. So that's going to give me a 1 minus x to the power negative 2. And I'm also supposed to multiply that by that original power, okay, according to the power rule. Chain rule says since there's stuff inside here, I'm going to multiply by the derivative of the inside. What's the derivative of 1 minus x? Negative 1. So I get another negative 1 to multiply. So cleaning that up, I get 1 over 1 minus x squared. Okay, term by term differentiation on the other side. I also need to take the derivative with respect to x of all those guys. So, well, derivative of 1 is 0, and derivative of x is 1. X squared, that would be a 2x. I left off the x cubed, but I'm going to write it in. That would be 3x squared. Derivative of x to the k should be kx to the k minus 1. Keep going. So I'm going to summarize that on the next page. So now I know that 1 over 1 minus x squared, oops, like that, is equal to the sum of k times x, oops, x to the, that's a bad x, x to the k minus 1, let's see, as k goes from 1 to infinity. Double check that I got the starting point right there. If I plug in 1, I get 1 times x to the 1 minus 1. Plugging in 2, I get 2 times x to the 2 minus 1. Plugging in 3, I get 3 times x to the second. Does that look like what we did a minute ago? Okay, so I got that right. I'm almost where I want to be. The next thing I need to do is multiply this sucker by x. Why? You'll see. So I'm going to make another series by taking x times this sucker. And so then I'm going to get the sum as k goes from 1 to infinity of k times x to the k. Right? Multiplying by x gives me x to the k. What does that look like? Well, it looks like this. X plus 2x squared plus 3x cubed. Now, just a check on this thing. The original interval of convergence was absolute value of x had to be less than 1. I differentiated that, and so when you differentiate, you retain the same interval and radius. The endpoints are unknown, though. Okay, so we do have to check the endpoints. Endpoints here would be plus or minus 1. And you can kind of plug in and see what happens. If I plug in 1 here, I get 1 plus 2 plus 3 plus 4. It still diverges. If I plug in a negative 1, then I'll get negative 1 plus 2 minus 3. We did that the other day for a different series. That didn't turn out so well either. So it diverges at both endpoints still, but you never know until you check. Here's the number I want to plug in. X equals -1/3. Because then I'll get the following series. I'll get -1/3 plus 2 times -1/3, which would be 2/9. Then I'll get a minus 3 times -1/3 cubed, which is 3/27. And then I'll get a plus 4/81 and a minus. Does that look familiar? Yeah, this is the opposite of what we ended up with in class. We tried to do this in class a few days ago, and it added up to 3/16. This guy right here adds up to -3/16 is my claim. How could I be sure? Well, plug -1/3 in there, because that's what this sucker's equal to. So let's do that together. So -1/3 divided by 1 minus -1/3, square the denominator. All right, so let's see. That is -1/3 over 1 plus 1/3 would be 4/3. Squared would be 16/9. So -1/3 times 9/16 gives me -3/16, which is what we predicted. Remember, we did like what, 100 decimal places or something? No, we did 50, I think, in class. And we were pretty sure it converged to 3/16. Now, the only difference here is I have the opposite, okay? So I could just fix that by multiplying by -1 and everything works out nice. So now that we have these functions that represent series, for a lot of the problems we did before, we could say it converges or it diverges. Now we have a whole bunch of functions that can help us find those values it converges to, which is kind of nice. The other thing we're going to generate with this is new functions that didn't exist before. Like, remember, sometimes when we integrate certain things, we couldn't find any antiderivative, hence we created a new function that didn't exist before. Same thing's going to happen here. So we'll play with that in the next few classes. All right, so we are up through section, what, 10.9. The homework for 10.8 and 9 is Monday. Please start on it before Monday. That would be a good idea. We're going to continue to work on 10.9 in class on Monday. That's our main focus Monday. More of this stuff.